I'll get started with the introduction, so then Frankie can start on time. So, welcome to the Environmental Research Institute seminar series. My name is Charles Lee. I'm the director of the Environmental Research Institute. It's my pleasure today to welcome Dr. Francois Thoreau, Frankie Thoreau. So Frankie is a postdoctoral fellow with us at the School of Science, although many of you have not met him because he is physically based in Wellington and Niwa. Frankie is working with Chris Battershall on the Ākau project, the Ridge to Reef project funded by the MBIE Endeavour research program to build a sustainable future for coastal reef ecosystems. So without further ado, here's Frankie and seminar.
Thanks for the intro. I'm just going to start this little video here. Kia ora koutou, ko Frankie toku ingoa. No wiwi oku tipuna, kei te noho o ki pōneke. So yeah, my name is Francois or Frankie. I come all the way from France and I've been living in Aotearoa for the last 7 years. I did my PhD at the University of Canterbury in Christchurch, and I was also based at Niwa in Wellington. And now, yeah, I'm very lucky to be doing a postdoc, PhD done, with Chris Battershall. There is a little video playing now showing roughly what this talk is going to be about. And what you see here, hopefully you can see it nicely on the screen, but it's what we are trying to study. There are those marine dark waves. It's the influence of sediment on coastal ecosystems, like a nice, beautiful kelp forest here. And they are quite important because we sort of argue that it is one of the most important extreme events driving coastal ecosystems around the country and also in other parts of the world. So what's sort of wrong with sediments in the coast? Well, they basically create this. They create periods of darkness underwater, more or less long, and that's quite a bit of an issue for kelp, which need lights to grow. And when we look at things from space, this is the sort of coastal features we see. So this is an image taken by the satellite called Sentinel-2. This is sort of on the Bay of Plenty side of Escape. That's the Raukokore Awa around Waiho Bay. And so there's quite a few features here on this image. But what's sort of very striking is the brown patch. So these are actually sediments that are being brought by the rivers in the coast. And on the right-hand side, what you can see is a picture taken on the ground from our partners from Te Whanua Apanui. And you can really see that distinctive brown patch of water. And if you were a kelp, for example, living on the seabed, you would basically have no light at all because the light is being obstructed by sediment in the water column here. You might actually recognize the white church from the movie Boy, if you're familiar with it. And so this research is, sort of an integral part of the MBIE and Endeavour Fund, led by Chris Battershall, which basically what we're trying to do is, because these sort of extreme events, these marine dark wave, they are due to sediments, so they actually originate on land. So the whole challenge is to try to bring what we do on land to what's happening in the sea, and doing so by sort of bringing together different knowledge systems. So we use what we try to say cutting edge scientific tools, but also we are trying to find sort of to weave it with Mātauranga Maori, and it's it's a challenge, but it's definitely an exciting challenge. So at the moment, we're mostly doing in situ research in Te Whanua Apanui Rohe. But yeah, we are currently trying to expand to other bits of the coast. So yeah, let's come back to the issue of sediment and kelp. Well, like sediments, when they are being discharged by the rivers, they create basically periods of underwater darkness. So they reduce the amount of light, both the intensity, but also the spectral shape, so the colors of light reaching the seabed. They can also smother and bury reefs, so they can bury underwater forests. And the thing is, light is very important for kelp because it's basically their way, the way that the energy gets into the full ecosystem there. And there is quite a bit of evidence that the underwater light environments across the country, has been like compromised and has been compromised for years, if not century. But there is a good thing. It's something we can do something about, at least on paper. Sediments, they come from the rivers, and before they end up on the rivers, they come from the land. So there are potentially certain land uses that creates this release of sediments. So unlike other extreme events like marine heat waves, for example, it's a bit tricky. For example, if we want to like manage marine heat waves, we need to cut down CO2 emission and other greenhouse gases. So it's kind of like a global challenge. Whereas here, marine heat waves and darkness on the coast, these events, they can actually be managed on a local scale, which is pretty cool. And this talk is about how, like, certain tools we can leverage at a national and local scales to try to find solution there. And especially, we're going to focus on the role of remote sensing of ocean color and also in situ. Then I'm going to sort of explain why we're trying to come up with a sort of like new framework to try to describe these extreme events. And at the end, I'll briefly touch on what's the next step that is about trying to link what's happening in the catchments to what's happening in the coast and really tell this story about how forests on the land are connected to the forests in the sea. So the sort of like, when we talk about the issue of sediment in the coast, that's definitely not a new topic here. And if you look like sort of at the scientific literature about it, the sort of like main concept is called coastal darkening, and it has a bit of a loose definition. Like, broadly speaking, it means long-term changes in how clear the water is. But yeah, and what you can see in one of the graphs is sort of like it is a term that is receiving quite a bit of attention. So I think this is the number of citation per year. I think it's from like 2016. So it's definitely something that people are doing current research on. But yeah, what's been sort of hard is that there is no actual definition about them. There's no way, there's no current like quantified way to measure it, and also it doesn't deal with light level. It talks more about water clarity, and of course underwater light is like really depends on how clear the water is, but it also depends on all other things. So here, I'm going to show how sort of we can leverage satellite remote sensing to help quantify what coastal darkening is. So what I've been doing during my PhD with Matt Pinkerton based at NIWA was to derive national scale underwater light estimates, especially irradiance on the seabed, so the amount of light on the seabed all around the country using ocean color remote sensing. And to do so, we mostly use three main ingredients. The first thing we need to model the amount of light and observe the amount of light on the seabed is to know how much light there is on the sea surface, right? So that's like what you see here. That's one of the satellite products. You also need to know how deep the water is through bathymetry charts. And last but not least, you need to have a measure of how clear the water is. And we sort of derive this information through a parameter called the attenuation of light, KD here, which is sort of like the inverse of how clear the water is. And when we combine these three, we can have national maps of the amount of light reaching the seabed in space and time. So what you see here is, exactly the amount of light on the seabed, sort of monthly climatology. So this is the last sort of 20 years average per month. So you see this sort of like extension and retraction of the amount of light available. So this is mostly due to just how seasonal light is. Not really, here I'm not really showing the impact of coastal darkening. And the cool thing is, because we rely on a satellite called MODIS Aqua, which has been going around since the mid 2002. So it's like more than 20 years of daily, at best, images, and with a 500 meters spatial resolution, which is cool, but also coarse at times. And thanks to this quite extensive data set, we can sort of investigate if there is more or less light actually reaching the seabed, and especially focusing at rocky reefs environment in the coast, where marine forest of kelp would be living. And so this is the sort of like information we can actually derive. So this is the at the national scale, the amount of rocky reefs. So this is in square kilometers that is receiving more than a certain threshold of light. And this is sort of thought to be the minimum amount of light for kelp to grow. And you can have this information also by season, breaking it down. And this gives us some sort of idea that things might be changing. For example, you see a bit of a upwards trend in summer, so potentially there might be more like suitable habitats over the last 20 years that could be suitable for kelp, although there is quite a lot of year to year variation. And sort of like contrastingly, when you look at the winter plot, this is a suggestion that winter condition might actually be becoming worse. So we might be losing some habitat for kelp. However, when you look at the sort of patterns in space, it's quite tricky, and this is sort of expected given how sediment is an issue that is very localized. It's really like all these trends are likely to be driven by catchment processes. So looking at national patterns is one thing, but at the end of the day, we really want to drill down to the catchment and to the local scene. And also what I haven't told is that relying and sort of leveraging ocean color remote sensing is also very potentially powerful, because it allows to also drill down and try to understand what are the drivers of seabed light. So whereas that is water clarity, or the type of optically active constituents in the water, that could be phytoplankton, or that could be suspended sediment, for example. And to come back to the sort of like main current framework that talks about this coastal darkening framework, the other I've been just talking about how there is no currently like quantified ways to measure coastal water clarity. And then, so here, what I've just been talking about is that here we can actually leverage ocean color remote sensing to measure how things change in space and time. And the other sort of like thing that the coastal darkening concept is missing is it's typically not an event-based framework. And by this, I mean that, say, sediments, they are usually brought in the coast following heavy rains. So it's really like a pulse. It's very like event-based thing. And so we need something that is able to measure this and is able to attribute and detect events. So that's where the marine Darkwaves framework comes into play. So yeah, so now we're currently trying to push for the recognition of marine Darkwaves. And so if you have heard about, for example, marine heat waves, it has some sort of like quite a lot of analogy. There'll be more a marine cold spell, which means we try to relate the current light level that you're currently measuring. We're trying to relate this to a long-term climatology and see how different it is. So currently a marine dark wave would be an event when the underwater light is at least below the 10th percentile. So it's like really a low light level compared to what should be. And it's at least for 5 days. So it's a sustained period of darkness, or at least very low light. A bit like the marine heat waves, for example, that's at least 5 days of the temperature being above the 90th percentile. And like having a sort of coherent and quantified definition would really help drill down their drivers. So what's causing them, how long they happen, is there the different things that's causing them, and more importantly, what are their impacts? So having having quantified metrics will really also help experimental work, trying to recreate them and try to link metrics that we can reproduce in the lab to what we can actually observe. And more importantly, what can we do about them? And that would also be a very nice way to see if what we are, the things that we're implementing to reduce marine dark waves, how much are they effective? So to sort of like try convince, at the moment this framework is sort of under review. So we're really trying to convince the scientific community that this is a thing and this is really important. So to do so, we've used one of the longest in situ time series of underwater light, because it's actually really hard to measure light. Underwater, you need to have a sensor that is sort of like strong enough, and you need to clean it because things grow on it. So it's actually really, really hard. So in California, they have a very awesome program, the LTR, which is a long-term sort of observational platform. And they have been measuring underwater lights since 2008. So we have been able to really apply this definition of the marine dark wave, and we have identified events. And yeah, it's still like sort of, we're still trying to really understand what's going on, but we definitely see quite a lot of events across an in situ time series. And you can actually see on this figure here that after the year 2020, there have been quite a lot more events on the Californian coast. And yeah, and at the moment, it's only like, we're just talking about hypothesis, but that might be due to like all the crazy fires they have had, and then the also like the very big runoff and flooding they have had there as well. And but the sort of one of the end goal is actually to try connect ocean color remote sensing and seabed light remote sensing to this marine dark wave framework, and have in space and time, where are dark waves happening. So what you see here on this map is still the sort of escape side of Bay of Plenty, and the Tairafiti coast. And you can see that we've been trying to apply the marine dark wave framework to ocean color remote sensing. And one point that really like sticks out is really that year 2023, which is like the last year on the record on this time series. And this is potentially due to Cyclone Gabrielle that has driven a lot of marine dark wave days because of the crazy runoff it has done. And you can also, this is another way to look at it. What's plotted here is the year of the most intense marine dark wave along that coast. And the prominent color you see here, especially on the sort of East Cape side, is that red colors that is indicative of the year 2023. So really that cyclone Gabrielle, big impact. And coming back now to not only relying on ocean color remote sensing, because it comes with, it has a lot of utility, but also a lot of limitations that we can definitely talk about after. And coming back to the Ākau research program, we've really lucky to be able to partner with some hapu in the Te Whanua Apanui, Rohe Mohana. And so, yeah, we are, measuring lights there, trying to really capture those marine dark wave events. So I don't know if you remember, before there was a satellite image of a really big satellite plume, sediment plume. And yeah, we're really trying to understand on a very high spatial and temporal resolution how long they last for, how far they go, because this is a really big concern for the communities there, because it's threatens their their relationship with the sea. And trying to slowly wrap up. That might be my break time app that is telling me to take a break. That's actually a good call. Anyway, we have also, so now the goal is to also connect what's happening in the sea to what's happening on land. And to do that, we have sort of came up with a spatial framework as well to really have a consistent way to measure coastal water clarity at river mouth, because this is going to be a crucial sort of it's going to have a crucial role into really connecting what's happening in the catchments, for example, certain land uses, how do they relate to like periods like marine dark wave. So for example, people talk about how forestry might really impact dark waves. So yeah, but it's still like, it's been really hard to show this link. So yeah, we really hope that using this type of framework, we can sort of really see how different catchments are and how different type of land use might contribute a different way to dark waves and their ecological impact. And talking about like future research opportunities, well, yeah, as I was just saying, one of the end goals is to really help how we like what we do things on land, and how we can just be like smarter about how we plan things, where we do have cattle, where can we do forestry without damaging the rivers and the coastal ecosystems. So that's like one goal. Another like cool research opportunity that we haven't been too much. We haven't done too much, but I think it has a lot of opportunity, is to really augment the use of ocean color remote sensing. One of the big issues is that we live in Aotearoa, the land of the long white cloud, and when it's cloudy, you can't see the ocean, so you can't see how clear or not clear the water is. And the issue is that usually when we have a big storm event and it's raining, it means it's cloudy. So we actually miss a lot of extreme events. So yeah, we've got to be smarter, and it will really help to develop some like AI smart gap filling techniques, trying to pull together rain activities, catchments, model. So yeah, a lot of work to be done in that space. And yeah, another thing that I'm really excited about is to try really like use that extreme events name, marine dark wave, that hopefully sounds catchy enough to really be able to like raise awareness about an issue that has been going on for years and years. And one of the big inspiration was really the marine heat wave, which has like, before people sat down and invented that term, not many people were talking about the ocean heating up and these like big events that were sort of threatening ecosystems. So that's like the hope here, that first we hope the scientific community will be kind enough to accept the sort of like term, and then we can advertise it to the wider society through social media workshop and all that, hopefully collaboration with artists as well. So that's the little clip you saw at the start. We are really trying to capture how visual it is, and that's actually a strength to when we talk about it. It's really a visual thing, whereas the marine heat wave, for example, is not really visual. So so on that note, I thank you all for your attention. Also, big thanks to all the people here that are involved in this program. Massive thanks to our iwi and happy partners too. We wouldn't be able to measure Darkwaves without them. And thanks to the people online as well. I can't really see you, but I'm sure you're here still, hopefully. And thanks heaps.
Let me just quickly check whether there are questions online. Yes, there is one. So the question is, how do you, you guys can read.
So the question is, how do you differentiate coastal areas which may be natural high in sediment in extreme darkening from impacted catchments? So that's definitely a really good question. I think one of the answers is that we are trying to, we're not especially interested in seeing what contributes the most to marine dark waves in terms of what is the main contributor to how clear or not clear the water is. So that's why we focus on this parameter called the attenuation, the light attenuation coefficient. But it's true that it is something that we're definitely really interested in, and the algorithms we use to derive water clarity, there are sort of like semi-analytical. That's sort of like their names, and by essence, I don't want to go too deep there, but by essence, they really try to differentiate what contributes to water clarity. That could be phytoplankton, that could be sediment, so dissolved organic matter, or that could be particulate things. But yeah, it's definitely a tricky thing, but overall, they all contribute to light attenuation. So not sure if I was really clear, but Ian is asking, is there evidence from other parts of the project that a 5-day extreme event has ecosystem consequences? Yeah, that's definitely a critical question. And I think it's a, so basically the question here is about how we are trying to use somehow a threshold that some people can think is a little arbitrary. Why 5 days? Or not three days, you know? And there is definitely evidence. So like first, I think we're really trying to have a general framework that is not linked to one ecosystems. So we're really trying to come up with a framework that can be applied for coral reefs, for sharks, for marine mammals. Everything in the ocean that doesn't live like really deep will interact with light. So might be affected by these marine dark waves. So yeah, that's why we are. It's a bit of a tricky thing to try. Impacts the definition of a broader, which actually it's more a physical process we're trying to characterize here. But there is definitely evidence from experimental work that 5 days, for example, darkness, period of dark, they actually do affect kelp for example. But yeah, it's still like really hard to find experimental work that have really been able to reproduce those darkness events, and it's hard. So Ian, did I sort of answer your question somehow?
Can you hear me if I speak?
Yeah.
Okay, that'd be easier.
You go ahead.
No, I was just kind of curious what else is going on within the project to kind of look at that issue. If you're thinking just about kelps, then 5 days is quite short for a kind of a physiological response. And I guess it's really nice drawing the parallel between heat waves and dark waves. But the mode of action of them, I think, might be kind of different in terms of, one's a kind of a reduction in a resource and the other is an imposition of a stress. So yeah, I'm just kind of curious. It sounds like a really great concept, but like you say, then providing evidence that it's of how it's impactful is a challenge.
Yeah. Thanks, Ian.
I guess I had two points. Well, I had Ian's question as well, so I'm glad you asked that. So do you distinguish between I can see this sort of relates to Chris's point here. So not only are you darkening, you've got two things going on, right?
Yeah,
the sediment, you've got the potential smothering of the benthnic environment when it deposits, if it indeed does deposit, depending on how fine it is. And then you've also got the darkening of the water column. So you've got sort of benthic and pelagic effects. Do you distinguish between those? Is there? I guess that's sort of related back to Ian's question about this idea of five days. I mean, maybe it's not a time thing, but maybe is it the water column darkening or is it the smothering that's the biggest ecological problem?
Yeah. No, for sure. I definitely don't have a straight answer, but the coastal darkening and the marine dark wave, these two frameworks, I think they address more the impact that sediment has on the light environments. They don't really try to answer the smothering action. And maybe like in some places, it's just the smothering is actually more important. So yeah, it's.
I guess I was going to make one more point as well, that if you using AI to do some gap filling is potentially quite powerful, but if you could also, something that would be a really nice addition would be to actually take a process-based numerical model.
100%, which has been there is definitely some work, for example, led by researchers at NIWA, I think in the Firth of Thames. They have done some like cool work, but I think the missing piece is actually, let's say, coastal oceanographers. Maybe they don't treat optics. Maybe they don't consider enough optics, and like it's actually really hard. Light is a tricky thing to work on. But yeah, it's I think that is definitely one avenue, is to like really tie all those expertise together.
Any other questions? Georgia?
Thanks, that was really interesting. I know you're more on the remote sensing side of things, but do you know if it's been found if there are any like changes in temperature, salinity, or pH associated with these big pulses? It seems like that could be something that might have an additive effect beyond just the light change.
Yeah, 100%. I think that's where we are missing a lot of observation and in situ work. So yeah, like I think the short answer, no, I've got no idea. But yeah, it's on paper. yeah, for sure, it's kind of fresh water plumes that are sort of being discarded in the sea. So yeah.
There's a lot of marine work done around Santa Barbara, so it's possible those data sets would be available.
Yeah, sure.
You
know,
yeah. Along with the other LTR data.
Only for not for long from this way.
Yeah.
Well, we gotta get the data while we can.
Yeah, for sure. Yeah, no, definitely the LTR data set is definitely awesome, and yeah, there's so many questions that can be asked around them. So stay tuned for more.
The questions? I have a question. I actually have a series of questions.
Fair enough.
So, obviously, one of the big challenges with optical with remote sensing the visible spectrum is clouds.
Yeah.
Another issue with that technology is that technique is waves.
Yeah.
So have you done any work to look at the potential correlation between waves and light penetration and darkening?
Yeah. I think that's definitely a great point, because one of the driver of coastal water clarity is definitely resuspension of sediments. So yeah, the short answer is I haven't done anything so far to try link the wave action, the wave environments to the light environments.
Yeah, because to me, wave is a critical linkage, right? Because that could explain Ian's 5-day question, because it may be that you have an event, but it's the churning that keeps the sediment from being suspended.
Exactly. Yeah.
There's also the fact that waves then messes with your they mess with your color-based detection.
Right.
And so one idea that just came to me, and kind of answer the question, is whether you've thought about using synthetic aperture radar to get the wave data and then superimpose that onto the optical data you have.
Yeah. I feel like that would be a serious amount of work. But yeah, it doesn't mean that it shouldn't be done, of course. I think I feel like if the question is about trying to see what we don't see, so like for example clouds, but then also, of course, wave action, especially breaking waves, they will make the algorithms fail to retrieve water clarity. So yeah, what's the biggest contributor to data loss? I wouldn't think that waves are a massive one, but still they are a crucial one to so like they're more like maybe like they're more of a driver of coastal water clarity than a driver of data loss. I would say.
Okay.
Yeah.
Well, maybe. So I mean, it's your problem is the fine sediment, right?
Yeah.
So your waves your fine sediment is not going to. Well, it depends how fine it is, but it's likely not going to settle out anyway.
Yeah.
In or not within. I mean, if you work out the settling speeds and the sort of current resuspension speeds, even probably without waves, you'd probably find that depending on where you are on the coast, you might things might not be settling very quickly anyway.
I mean, sure. And I mean that's when we really need to have this like sort of long-term and high frequency in situ lights measurements, and we definitely do see from like the first few months of data we have on the sort of like escape side. Is
the sediment mostly sandy out there, or is it mostly muddy?
Sort of mostly muddy.
Okay.
Yeah. So like it really comes and go. So I think it fuels the story that, you know, ideally the water should be always clear. You know, and because we have messed with a lot of processes on land, you know, like all this input of sediments shouldn't be there. I mean, like it's kind of a tricky thing to say, but so yeah, I think it's really mud.
Okay, one more question from Ian.
Yeah, so Ian is talking about how the algorithm perform in this type of water, where so he's referring to case 2 waters, which is actually the water where you've got phytoplankton, suspended sediment, and also things that are dissolved as well. So there's a lot of things that interact with light. and this sort of opposes to case one waters, which is what we find offshore. Offshore, there is the only things that usually interact with light is water itself and phytoplankton. So there's not that like influence of things from the land mostly. So, and to answer Ian, we do try to use the most sort of case-2 friendly semi-analytical algorithms. So they are supposed to cope well enough to these sort of optical conditions, this case-2 waters. However, there's still a lot of work to do in trying to like really validating them, and especially in New Zealand waters. So yeah, like it's on paper, it's supposed to be sort of the best thing we can actually use. But yeah, I feel like we need way more work in trying to validating them at a national scale.
Okay, any more questions for Frankie? No?
I had a quick one, Frankie, if you can hear me. And we've talked about this, just the nature of the sediments themselves. And I know you've been concerned about this. Has there been much more done on the sedimentary type that's getting discharged out into these various coastal systems? Because some sediments will refract or reflect light differently to others. Just thinking about your the national modeling that you've done.
Yeah. So about the national framework, we definitely we have picked up how different coastal water clarity are across all the river mouth at national scales, and we've tried to relate this to how the sort of like coastal morphologies of river mouth as like one case study. But now that we have sort of like this framework in place, we could test for other things like what's the sort of like typical geology of the catchments. So yeah, the answer is like we haven't done much in this space, but we are getting closer to hopefully doing it. Diplomatic answer.
Can't do it all at once.
Yeah. I mean, and like that's when like there is definitely some good work around the country about catchment based and the sediments, the type of sediments are they catchment based. Some good models around the country, but yeah, it's still we haven't done the effort to try to link it with the optics, and especially at the coast.
Yeah. Thanks.
Thanks, Chris.
Great. Any more questions? Yes.
Right. Talking about the like average seabed light levels that you were seeing over years, and it was like maybe getting more in summer and spring, and then maybe less, like a bit more clear, less in autumn and winter.
Yeah.
Is that more from like weather that you were seeing, just like the amount of light that was allowed to reach, or sediment movements, or do you know kind of what was kind of driving them?
Yeah, I mean, like, I think when we look at a national scale, it will be just a blend of everything, you know. So that's why we need to drill down at sort of like catchment scale or local scale. So yeah, it's in some places it's the like more sediment being brought down. In other cases, which is like it's actually more like it's more like the phytoplankton. So like there might be more or less sort of phytoplankton around them, which can be due to like the currents changing a little bit. So it's really a complicated thing. So so far we haven't come up with a sort of national map of what's driving light. But yeah, I mean, we have, but we haven't really like understood it well enough.
One more.
Thanks.
Can I ask a stupid question? Your video on the front side.
Let's watch it again.
Yeah, what?
I'm glad you asked me that. Yeah, 100%.
No problem.
So it's actually a French artist called Cassandra. She's currently based at NIWA in Wellington, and she's really interested in trying to use visual things to explain scientific concepts. And so here she's done a crazy cool layout where there's actually a projector that is projecting a beautiful AI generated, we're going to change that, kelp forest. So she's projecting it in a plastic sheet that is in a aquarium, and she's just putting some baby chalk on the surface. So that's what's sort of like making it's kind of hard to see here.
So do we think this is giving people an accurate representation on what coastal darkening might be? That's my question.
Yeah. I mean, I feel like first, why do we want to represent something accurate? Given that, I think it's more about making people relate to the issue. And we can do it either by trying to be like sticking to what's happening really underwater, or just, like illustrating in a way that people can make sense of it in their mind, so then they can relate and care about it. So I'm not saying that we should do something outrageous, but this is sort of like pretty good to me in terms of like things come from the sort of like surface and settle down, and sort of like just makes the water darker. We also want to change sort of like how the colors, underwater colors actually changes as well, like to really illustrate how, like sediments also interfere with the spectrum of light. And of course, then you can argue that, it's bullshit. But yeah, it's, it's like art science, right? Like we're not, I mean, it's definitely a big debate, but, we're just trying to give people an experience of what's happening underwater, knowing that not everyone has had the chance to put.
Or just showing somebody a black screen.
Yeah.
Well, actually.
I think one thing is that even as scientists, if we stick to using only real footage, often we editorialize and pick the most dramatic ones.
Yeah.
Right. That aren't necessarily statistically representative because we're trying to get a point across.
Yeah.
So I think as long as we're not reaching falsehood,
for sure,
having visual aid is not necessarily involved.
But
No, I was just curious.
for sure, because I feel like like we all have biases, right? And to me, I understand this issue through mostly satellite images, so like 2D from the top, and like I that's the way I understand it and the way I see it the most. But it's actually really hard. Like when you show someone a satellite image, they'll be like, what should I look at? There's so many things going on. Like it's just not everyone is trained to have a look at this issue from this angle. So like I think this is a bit more like catchy at least. And
I thought the photo of the brown and the blue was very striking.
Yeah, for sure. Yeah, for sure. I think it's like this one, like this is definitely also.
Right. That's pretty.
But yeah, of course, and I mean it's a cool thing, and I really hope in the near future I would love to be involved in like research projects co-designed with, for example, artists involved at the start, because I think it's really awesome the way like when I'm interacting with Cassandra, it just challenges me like to really try to explain what's going on, and she's always like, what, like the colors on the seabed, they change, what, like it's kind of really, really cool. So yeah, I think like, and also having more fun, really, like sitting on a computer is cool, but it's kind of sometimes not as cool as hanging out with people that are like that have creative brains and you can Sorry, went on a bit of a tangent there. Thanks for your comment tonight. It's good.
Yeah. So just coming from the call. Okay. Thank you for coming to the seminar. Frankie is going to be around for a few days. You can look up his email address in the system. So so if you want to reach out to him and talk more, please just get in touch. So I have something to present to you. as a token of our appreciation for giving this
Awesome.
talk.
Thank you. Thank you very much. And yeah, thanks everyone for coming here. It's always a bit, overwhelming coming here and not knowing anyone. But now we do know each other.
Right. So Chris is giving her first-hand account that it looks real enough.
Oh yeah, no.
Thanks, Chris.